Hello everyone, my name is Jeff Rexford. I'm an electronics engineer, about 40 years of experience, and some of that has been in the recording industry. One of the things I want to talk to you about today is sound visualization. This is a field that we've, as engineers and technicians, use quite a bit. A few things we're going to talk about today are why do we need visualization sound, or why do we need to visualize sound in the first place? Useful examples of sound visualization. The three major methods of visualizing sound, that is the oscilloscope or the O-scope, spectrum analyzer, and the spectrograph or spectrogram. And then we're going to use some useful demonstrations on how each of these work. Well, visualizing sound in a graphical way can help us identify things. We can see things that our ears can hear it, but really can't identify what it is. So visualization helps us identify wanted or unwanted elements in our sound envelope or our audio chain. Few ways we can do this and few ways that these visualizations can be useful. Troubleshooting sources of noise. Graphical representation can sometimes give us a really good clear indication of the source of the noise or what type of noise there is or even where it begins. Listening sometimes just can't do that. You can hear the noise, but the visualization can really help identify these things. Biasing amplifier stages is immensely important because quite often our equipment doesn't come calibrated correctly. And I've had people bring me very nice pieces of equipment that they just weren't having luck with, that they said just didn't sound good and they couldn't use anymore. And the only thing that was wrong was somewhere in the amplification chain was an unbiased or a not properly biased stage that was causing distortion or not a proper representation of the sound flow through. So what you put in and what you got out was not what was expected. Then you've got setting and adjusting EQ filters. And this is immensely helpful if you're trying to dial in a particular sound. And it's difficult to do a complicated sound chain when you're trying to get something very specific in your sound. But visual representation can really help a lot. Reproducing amplifier room synth sounds or modeling. We have people now that will take sounds, recordings from a particular room or a particular amplifier and speaker combination. And by looking at that graphically, it makes it much, much easier for them to dial in if they're trying to somehow simulate that and try to capture that same type of sound. And the next is evaluating some microphone response curves, which helps a great deal when you're trying to evaluate your microphones. You can have microphones from the same batch, same manufacturer, same model number, but they can be sometimes different. It'll help you identify and tag so you can have specific microphones set for specific instances. Okay. So there are three major methods for visualizing sound. There are others that are out there, but these are the three main that would pretty much cover everything you can think of or every aspect or every need you would have in troubleshooting or optimizing your sound chain. The three are the oscilloscope, the spectrum analyzer, and the spectrograph or the spectrogram. Now, all three of these utilize almost the same functions. They use amplitude and they use frequency. And the easy way to look at this representation is the oscilloscope and spectrum analyzer are almost the same. They both use amplitude for vertical and they use time or frequency for the horizontal. And the only difference between the two is the oscilloscope uses a time slice that's the reciprocal of the frequency, and the frequency is the horizontal of the spectrum analyzer, and that's the only difference. So if you were to look at a signal on the spectrum analyzer that has a 1 kilohertz frequency, you take the reciprocal of the 1 kilohertz frequency, and what you would see on the oscilloscope is a sine wave, and the sine wave would have a peak-to-peak period of 1 millisecond, which is the reciprocal of 1 kilohertz, and that's really the only difference. But to really look at a pure waveform when you're testing amplifier circuits, it's great to put a pure waveform through of a particular frequency and then look at the different waveforms at the different stages of amplification and attenuation to make sure that that stays pure. If you see a deviation in that waveform, you know that you're introducing some form of a distortion. The spectrograph can be considered almost a three-dimensional display because not just using amplitude and frequency, it also uses a time slice, and the time slice would be maybe show a 10-second time frame of a stream. And during that time stream, let's say it's a 10-second time stream, you would see frequency in the vertical, you would see the time stream as the stream moves horizontally across the graph. And then the color intensity would be the amplitude. So instead of just 2 dimensions, it's really showing almost 3 dimensions. And that can be useful, particularly in the area of things like speech recognition, where a computer has to look at a series of changing sounds and look for signatures to determine what those sounds are and try to identify the type of speech and the sounds and try to put all that together.
So here we can see a graphical representation of the oscilloscope, the spectrum analyzer, and the sonogram. Horizontal is in time slices, and you can see that time spacings are going from 5.33 milliseconds over to 41 milliseconds. So you can see you're looking at the period of the waveform, where the spectrum analyzer below you're actually looking at the frequency, and they're just a reciprocal of each other, and the vertical's the same. They're quite useful for different aspects though as well. So here we're going to put some signals through each of the elements, and this is a 120 Hertz signal. So you can see on the top of the oscilloscope is showing a period of about 8 milliseconds peak to peak, and that translates when you do the reciprocal for the spectrum analyzer down below to 120 Hertz. So as we reduce the amplitude, you can see the amplitude drop on the oscilloscope and spectrum analyzer, but on the sonogram you see the color change to blue or less intensity, and when we come back up, you see the peaks come back up on the oscilloscope and spectrum analyzer, and the intensity come back in the color for the sonogram, and if it was super loud it would start to turn yellow or red. Now as we increase frequency to twice the frequency, you see the sonogram move up over the time frame. The spectrum analyzer moves to the left to a double frequency of 240 Hertz, and the oscilloscope period reduces in half to about 4 milliseconds. And now we go back in frequency back to the original 120 Hertz, and you see the sonogram slide back down. No change in amplitude, but the spectrum analyzer moves to the right, and the oscilloscope opens up to a wider period as the reciprocal of the spectrum analyzer frequency back to 8 milliseconds. Now we see not a triangle wave, but a sawtooth wave. And you can see from the sawtooth wave, you can see the harmonics in the spectrum analyzer, but you can see by the deviation in the waveform on the oscilloscope that there's other things that are in there, but they're hard to identify on the oscilloscope because of the wave shape. But you could easily see them on the spectrum analyzer. So here you can easily see, as we transition to the sawtooth wave, you can see the harmonics come up, which is the even harmonics from the spectrum analyzer stepping down in intensity on the spectrum analyzer. From the fundamental is the highest, and then it steps down. But you can also see the results in the sonogram, where you have the different harmonics showing up there in lowering intensities as you move up in frequency, where the fundamental is the strongest, but it's giving up some of its energy to develop the harmonics. And you can see on the oscilloscope that you know that there's a waveform deviation here. You know that there's harmonics or some complication mixed into the fundamental frequency, but it's difficult to tell exactly what it is until you look at the spectrum analyzer and the sonogram, and you can break it down and see the actual frequencies that are included and the intensities of those frequencies. And as we reduce and go back to a fundamental frequency of a sine wave, we get back to a single peak again, and the sonogram dies out.